Okay, good afternoon. We are going to start on drives, lecture number 22. In the last class, we had looked at semi-converter fed separately excited DC motor drive, specifically three-phase semi-converter fed separately excited DC motor drive. And we had looked at what is the difference between three-phase full converter fed separately excited DC motor drive and with the freewheeling diode, and three-phase semi-converter fed separately excited DC motor drive. So what we said was, when we put a freewheeling diode, the negative portion of the voltage gets cut off, but average DC voltage in this particular case is going to be less than what is the average voltage in semi-converter case, because the negative portion, the negative half cycle of each of the phase voltages, that is not going to be controlled. So whatever is the most negative voltage that will come up, whereas the positive side voltage is controlled in this particular case, the negative side voltage is not at all controlled. Whereas here, both positive and negative side voltages are controlled. And only if there is a negative excursion in the DC link voltage, that is going to be completely eliminated. So in general, we are going to see that continuous conduction is more prevalent in semi-converter case as compared to the full converter with DFW. So if I try to look at which one will have a better possibility of continuous conduction, that is going to be definitely better in semi-converter as compared to the full converter with freewheeling diode. So this is definitely not going to have as much possibility as the semi-converter case. So in today's class, we are going to mainly look at three aspects. One is, today's plan for the lecture class, we are going to have three things discussed. One is three-phase semi-converter. We had not talked much about no load speed. So let me probably look at it once again. That is important. The second thing is we are going to look at series motor drive, because the series motor drive, the analysis will be somewhat different as compared to separately excited DC motor drive. And the third thing that we are going to look at will be dual converter. So dual converter is two full converters connected back to back. So when I connect two full converters in anti-parallel fashion or back to back, that is when we call it as dual converter. And this will be able to give 4 quadrants of operation. So this is going to be able to give us 4 quadrants of operation. So this is going to be basically our plan for today. So if we look at three-phase semi-converter, we said that was 3Vm divided by 2 pi multiplied by 1 plus cos alpha. This is what was our average armature voltage when continuous conduction is prevailing. And we said that continuous conduction is going to prevail in most of the cases because we have a good amount of voltage coming up for every 60 degrees in a semi-converter case. So if I again draw the waveform for the three-phase semi-converter case, so this is omega t, and let us say this is one phase voltage. So let me draw the second phase. So this is going to be the second phase voltage. And I'm going to have the third phase voltage somewhat like this. So this is going to be the third phase voltage, which is coming up like this. So let me call this as A, this as B, and this as C. And we already said that when B phase is negative, 6 is going to conduct. There is no control over it because it is semi-converter. It's only diode. This is C phase. So 2 is going to conduct during this interval. And we are going to have 4 conducting during this interval. And depending upon which device I am firing, for example, if I am firing device number 1 here, only 1 and 2 will continue to conduct. And if 1 is fired here, we are going to have alpha equal to 60. So alpha is calculated from this point. So if I have alpha equal to 90, for example, so if I'm going to have alpha equal to 90, this is the point where alpha is 90. So this is alpha equal to 90. So when alpha is 90, I'm going to fire 1 here. And 120 degrees from there, I'm going to fire 3. And another 120 degrees from there, I'm going to fire 5. So 5 is going to be fired here. So this is where 5 is fired, which is same as 0 degree. So this is where 5 is fired. So I should say 5 is fired here, 1 is fired here, and 3 is fired here. So when 1 is fired here, so we are going to have 1 and 2 conducting. So this is going to be the voltage that comes up right across the armature. And after that, 4 takes over. So 1 and 4 are going to conduct during this interval. So we are going to have 1, 4 conducting here, whereas during this interval, it is going to be 1 and 2. So when 1 and 4 are conducting, it is going to be freewheeling. So if I try to look at what is the kind of DC voltage I am getting, I'm going to get from here until here, where VAC becomes 0 at this point. This is going to be VAC. So this is going to be the sinusoid, which is starting from its peak value and goes down to 0 degree, 0 magnitude. So this is the complete quarter cycle of VAC. So this is alpha, and this is going to be alpha plus pi by 2. And from there, for another 30 degrees, you're going to have 0 voltage. After that, we are going to have when 3 is fired, so we are going to have this as the voltage that is coming up. So this will continue until here. So when I have 3 and 4 conducting, this is going to be BA. So this is VAC, this is VBA, and again I'm going to have 0 voltage coming up here. And during this portion, when I'm going to have 5 being fired, 5 and 6 are going to conduct together in this portion, and that is going to come up as VCB. So these are the 3 voltages that come up. And please note, this will be the peak of the line voltage, and it will come down to 0 after 90 degrees. Similarly, this will be the peak of the line voltage, and it comes down to 0 after 90 degrees. This is again peak of VBA, which is the line voltage, and it comes down to 0 after 90 degrees. So until alpha is less than or equal to 90 degrees, peak of line voltage will be encountered by the armature. Whereas if alpha becomes greater than 90 degrees, so let us say alpha is 90 plus 30, 120 degrees or something like that. So if alpha is greater than 90 degrees, then the conduction itself is going to be delayed by so much of time duration. So if it is delayed by, let us say, some angle gamma or something like that, this voltage is going to start from Vm sine alpha plus gamma. So if it is actually alpha is 90 degrees, then we said Vm sine 90 is the maximum voltage faced by the armature. Whereas if alpha is greater than 90, Vm sine alpha is is the maximum voltage encountered by the armature. So, if by chance back EMF becomes equal to Vm sine alpha, that is when no device can be fired, which means that is the ideal no load condition. So, we should be able to say for alpha ranging from 0 to 90 degrees, maximum no load condition or ideal no load speed is going to be corresponding to Vm line to line divided by K5. Whereas for alpha greater than 90 degrees, the ideal no load speed is going to be Vm sine alpha divided by K5. So just to indicate this in the speed torque characteristics, we should show it somewhat like this. So let us say this is omega axis and this is the TE electromagnetic torque axis. So if it is full converter, we actually drew this somewhat like this. This is for alpha equal to 0. And let's say this is for alpha equal to 30. Maybe this is for alpha equal to 60, whereas this is going to be for alpha equal to 90. So this should be droopy slightly. So I should show it as though alpha equal to 90 is like this, alpha equal to 120 is like this. So these are the different characteristics. And we said that for alpha equal to 0 and alpha equal to 30, it will have the ideal no load speed to be Vm by K5 for the full converter case. So these are all for full converter case. And for alpha equal to 60 onwards, we said Vm sine alpha plus pi by 3 or something like that. So we had something of this sort. This is what we were having as the characteristics corresponding to full converter. So this is also full converter. This is again full converter. This is also full converter. So all the blue color characteristics are for full converter. For semi converter, Vm by K5 will be the ideal no load speed for alpha equal to 0 until alpha equal to 90. So for alpha equal to 30, if I try to draw for semi-converter, this will be alpha equal to 30 semi-converter, and it should be again joined with Vm sine Vm divided by K5. Similarly, for alpha equal to 60, maybe I will have something like this for semi-converter, which will be lying much above the full converter case, and that should also be joined to this. Similarly, if I try to draw for alpha equal to 90, that will also lie much above the alpha equal to 90 for the full converter case, and that should also be joined with Vm divided by K5, which is the ideal no load speed. And if I talk about alpha equal to 120, maybe I should show alpha equal to 120 somewhere here. This is alpha equal to 120 degrees. And that also lies in the first quadrant. And that should be connected with Vm sine 120 divided by K phi. So this should be joined with whatever is Vm sine 120, Vm sine alpha by K phi. So this is Vm sine alpha divided by K phi. So you are going to see that the discontinuous conduction case is rare, but however, you're going to have the no load speeds determined based on alpha whenever the firing angle is greater than 90 degrees. And it is going to be constant at Vm divided by K phi when alpha is less than 90 degrees in semi-converter case. And always semi-converter speed torque characteristics are going to lie in the first quadrant of operation. So only one quadrant operation possible. Quadrant of operation possible. In the case of semi-converter, you cannot have even two quadrants of operation. Okay, so this is one point I just wanted to bring it to your notice. Fine. Now let us try to take a look at series motor drive. So what happens to a series motor drive when you are looking at its functionality? So if we are first, let's start with single phase fully controlled converter case. So if this is going to be the single phase fully controlled converter, which is feeding the series motor drive. So this is going to be the field and here is the armature. Both of them are in series and that is being fed by this fully controlled converter. And here is our source voltage. So this is A and this is B, and this is going to be single phase, maybe 230 volts, 50 hertz supply. Now this is T1 and this is going to be T4 and this is going to be T3 and this is going to be T2. And here is the field and here is the armature. Now our back EMF is going to have plus here and minus here, and this is going to be EB. And let us say this is the direction of rotation omega m. Now in this particular case, EB is equal to K phi omega m, where phi itself is a function of current. So we are going to have Vm sine omega t equal to Ri plus L di by dt. I will not write this as Ia because the current that is flowing through the field and armature both are one and the same. That's why I'm writing this as I plus Eb. Where Eb itself I can write as Ri plus L di by dt plus K dash multiplied by I multiplied by omega m. So this actually introduces the complication for us and we are not going to be able to get a closed form solution for the I value. So we will not be able to get a proper solution for the current. So if we assume that the time constant of this machine is going to be large, so we can assume probably that omega remains as a constant during half cycle or one complete 20 millisecond duration. So let us say this is my supply voltage and this is the rectified portion of the supply voltage itself. So this is omega t. Now this is alpha and let's say this is pi plus alpha. And if I want to draw the current, I should know how the back EMF is intersecting with the armature voltage. But unless I know the current, I cannot draw the back EMF because back EMF itself is dependent upon the current. So it's not going to be very easy to draw the waveform. But if I say that this is the kind of current I'm going to have, I'm just drawing the current as though this is how the current is. Maybe this is IA. So wherever we are going to have A like this, I should just draw the back EMF as a scalar multiplication of this kind of I. So maybe I will have, this is the kind of back EMF I'm going to have. So I'm drawing the back EMF somewhat like this. So this is K I omega M or K dash I omega M. So this is the back EMF. The green color waveform is the back EMF, whereas the blue color waveform is I. This is going to be I. And what I show in black is Vs, which is the source voltage. So this is going to be Vs. Now, where Vs meets the back EMF, that is where the peak of the current occurs. Okay. And you can see that the back EMF is again oscillating exactly in the same way as that of the current. So the opposition provided by EB to the current decreases as the current decreases. As the current itself decreases, you are going to have the opposition also decreasing. So this is one reason why the current may not become discontinuous very easily in this series motor drive. So in series motor drive, most of the times continuous conduction prevails. Why does continuous conduction prevail in a DC motor, a series motor drive? It can be attributed to the following three factors. One is opposition to the current provided by EB is not as strong as it is in the case of a separately excited DC motor drive, because EB itself is not a constant. EB is going to decrease, that is EB decreases when current decreases. That is why the opposition provided by EB to the current itself is small. So that is the reason why you are not going to see the current really reaching zero value very easily. The second thing is LA and LF both contribute to the overall inductance. So if the inductance is higher, definitely there is a better possibility of continuous conduction. So there is a better possibility of continuous conduction. So this is going to cause continuous conduction to take place, probably in a higher probability in a series motor drive. The third one we should also say is series motor drive is never run on no load. We already said this. If you run it on no load, you are going to have extremely large speeds. So series motor drive is always run on load. So I cannot be too small. So if you expect the motor to be on load, obviously the current has to be a fairly good amount of value. So that will also make it continuous conduction. So that is the reason why generally you would see only continuous conduction taking place in the case of series motor drive. So we might write actually there will be some amount of residual magnetism in the field circuit. So if we say that the residual magnetism is something like K res, so we can write back EMF equal to K res multiplied by omega m plus some K dash I multiplied by omega m, where K dash I is the field flux contributed because of the current and K res is the flux contributed in the form of residual flux. So this is going to be the total back EMF. So that is the reason when we write the equation, we should write Vm sine omega t when alpha is, when omega t is lying between alpha to, let us say, pi plus alpha in the full converter case. This is going to be Vm sine omega t equal to Ri plus L di by dt plus K res plus K dash I multiplied by omega m. So this is going to be the equation from which we can again write the solution, but it's going to be really difficult to find a closed form solution for the current because of this dependency of the back EMF on the current itself. So generally, how the series motor speed torque characteristics, how it is obtained. If you try to look at it, the first thing what we do for a series motor drive is to get a open circuit characteristics. So obtain open circuit characteristics by connecting series field as a separately excited field. So what we try to do here is, if this is the armature of the series motor drive, we disconnect the field from the armature and we connect the field to 230 volts or 220 volts DC supply with a variable resistance. So the series field resistance will be very, very small. So if we directly connect it across the 220 volts DC supply, the current will become extremely large. That is the reason why we will always connect an external resistance along with the field. So this is the field, series field. Okay. Now, by varying this resistance value, you will be able to obtain different values of current. Then you measure what is the kind of EG you are getting across the armature by rotating the armature with the help of a prime mover. So what you do is you connect the armature to another, couple the armature to a prime mover, and then you try to rotate that prime mover at a particular speed. And then you try to see what is the kind of generated voltage you are getting when different values of field current are flowing. And that if you plot, you will be able to get what is EG versus IF. So that will be the open circuit characteristic. So you may get it somewhat like this. With the residual magnetism, you may get some generated voltage and then it will reach saturation like this. So the field current itself will be same as armature current value. So that is the reason why it cannot be 1 or 2 ampere. It will be like 10 amperes, 20 ampere, 30 ampere, and so on. So this is going to be IF in ampere and EG in volts. Now from this, if you divide this by omega, so EG divided by omega m will give us what is the K5 value at different values of field current. So you will be able to get exactly what is the value of K5, and that variation will also be somewhat like this. So this will be K5, whereas this will be EG. So you have got K5 value corresponding to different field current values. Now, once we get, so K5 versus IF can be obtained from this open circuit characteristics. So once you get that, then what you would do is, for the full converter, assume a particular alpha value. Okay. And then assuming continuous conduction, calculate 2 Vm divided by pi cos alpha, which is average armature voltage. Once you get armature voltage, average armature voltage, now the third step is going to be assume a current value within the rated current. So if the rated current is 100 ampere, maybe you assume first 10 ampere, then 20, 30, 40, and so on. So you assume a current value within the rated current. Now calculate VA minus IA RA plus RF as EB. So you can calculate back EMF. So once you calculate back EMF, now what you are going to do is from K5 versus IF characteristics for the assumed current value, get the corresponding K5. So you should be able to get what is the K5 value by looking at the K5 versus IF characteristics, what you have obtained from the OCC. So you had divided EG by omega m, and then you had calculated what is K5. So you have the K5 value for every current within the range of the armature rated current. Now, at this point, once you have the K5 value, calculate PE equal to K5 multiplied by I, and omega m equal to EB divided by K5. So you have got both torque and omega. So you can say thus TE and omega m have been calculated at I1, the first current value, or at the assumed current value. Now, the next step is to assume another I value, which I may call as I2. First value, what I assumed is I1. So initially what I assumed was I1. Now it is I2. Then you can go to I3 and so on and so forth. So now you have to go back to step number 3. So after step number 6, you are going to go back to step number 3. So you can get what is TE and omega m for I2. Then you can get what is TE and omega m for I3 and so on. So you can say repeat steps 3 to 5 for I2, I3, and so on. So you'll get a series of points for a particular alpha. Now, if I want to look at it for a different alpha, then I2, I3 until rated current. Whatever is the rated current, you can completely do the calculation until the rated current. So once this is done for a particular value of alpha, now calculate VA for the next alpha value. So if you had assumed initially alpha equal to 15 degrees, then you can do it for 30 degrees, 45 degrees, 60 degrees, and so on. So once the next alpha is assumed, then at that point, you can again assume what is the current value. So now you have to do again, assume the another current value, and you have to repeat steps from 3 to 3 to 7. So you can say repeat steps 3 to 7 for this alpha. Do this until alpha is less than 180. So less than or equal to 180. So you are going to do it for alpha equal to 30, 40, 50, 60, and so on until probably alpha equal to 120, 150, and so on. So you would be able to get the characteristics offline for a series motor drive. A similar thing can be done for, so this can be done for single phase full converter, single phase semi converter, then three phase full converter, and three phase semi converter. So that you get the entire range of characteristics for the series motor drive as well as to how it functions. We will try to work out a few problems on series motor drive also when we are discussing problems on three-phase converters, converter fed separately excited DC motor drive. Along with that, we will also see some of the series motor drive problems. Now let us go over to dual converter. So dual converter is a configuration. Let me first of all show you in single phase case. So what we are going to have is on one side, we are going to have a full bridge converter, controlled converter. So which means we are going to have 4 thyristors being connected in the form of a bridge, and that is going to feed a DC motor drive. So this is feeding a DC motor drive. Okay. So this is the single phase supply. Now, if I want this to have all the 4 quadrants of operation, if this is circulating a current in this way, I want another converter to circulate a current in the opposite sense. If I want really this motor to work in both forward motoring as well as reverse motoring operation. So I will have 4 devices again connected in bridge format, but which is going to be exactly in anti-parallel condition. So I'm going to have this bridge also actually being connected to this um, armature itself or this DC motor drive itself. And I will connect both the bridges to the same power supply. So if I'm talking about this power supply here, that is going to be connected to the same terminal. And if I'm talking about this particular other terminal of the power supply, that is going to be connected here. So if I say this is A and this is going to be B and this is single phase 230 volts 50 hertz supply. So this A is connected here as well. So this is A and this is connected as B here. So if I may call this as T1 and if I may call this as T4 and if I call this as T3 and this as T2, I'm going to call the same way whatever is connected as the positive side of A. So this becomes T11 and this is going to be T31 and this is going to be T21 and this is going to be T41. So these are the four devices. Now, if I try to fire both of them in the same firing angle alpha, this will give me plus here and this will give me minus here, whereas this will give me plus here and this will give me minus here. So I can't really short circuit them. In that case, there will be a huge amount of circulating current. To avoid that, first of all, I have to choose the firing angle alpha 1 for converter 1 and alpha 2 for converter 2 in such a manner that this voltage, what I obtain here, if I may call this as VD1, I want this voltage and this voltage to be equal to each other. So I have to ensure that the two voltages are equal to each other, at least on an average basis. So I should say Vm 2Vm divided by pi cos alpha 1 should be equal to minus 2Vm divided by pi cos alpha 2. So this is converter 1 and this is going to be converter 2. And if I want this voltage to be equal to this voltage, please note this is plus and this is minus normally. That is why I'm writing this as minus 2Vm divided by pi cos alpha 2. So these two have to be equal to each other, means cos alpha 1 plus cos alpha 2 should be equal to 0, which gives me the solution that alpha 1 plus alpha 2 should be equal to pi. So if alpha 1 plus alpha 2 equal to pi, then on an average basis, if it is continuous current, I should be able to get VD1 equal to VD2 when I'm connecting them together like this. So I should say, if for example, if alpha 1 is 30 degrees, then alpha 2 should be 150 degrees. 180 minus 30, which is 150 degrees. Similarly, if alpha 1 is 60 degrees, then alpha 2 should be 120 degrees. Only then this VD1 equal to VD2 will be valid. Otherwise, it will not be valid. So let us first of all try to look at the waveform corresponding to alpha equal to say 30 degrees and alpha equal to 150 degrees. So this is omega t. And similarly, I have to draw one more sinusoid so that I can draw the waveform for converter 1 and converter 2. So this I'm going to draw for converter 1 and I'm going to draw for converter 2 here. So if alpha equal to 30, this is going to be 30 degrees. And I should draw it as though this is inverted like this. And this is going to be pi plus 30 degrees. So I'm going to have the voltage such that if I assume continuous conduction, I'm going to have the voltage such that, oh, so the entire thing is erased. So I'm going to just draw this once again. So I'm going to have this entire thing coming up here. And this is 30 degrees, pi plus 30 degrees. So this entire voltage will also come up. and I will have this voltage coming up here. So this is going to be the voltage that comes up when I am looking at alpha equal to 30 and this is pi plus alpha. So this is going to be the kind of voltage what I look at as VD1. Whereas if I'm looking at VD2, I'm actually looking at alpha equal to 150 degrees. So this is alpha equal to 150 degrees and I have to draw the inverted voltage of this. So this will be corresponding to pi plus alpha. So what I'm going to have, if it is continuous conduction, I'm going to have this as the voltage and I will have again this as the voltage and this will be the voltage which is coming up. So here also I have to have this as the entire voltage. So this is going to be minus VD2. So please look at what is VD2. VD2 is actually reverse of whatever is the normal positive and negative. So this is minus VD2. So if I invert this and draw, I should draw it as though I am having this entire thing and then from here it is going to have uh, uh, rest of the sinusoid coming up like this. And again, I'm going to have this coming up like this. So this is going to be the kind of waveform I'm going to have for VD2. So VD1 and VD2, although on an average basis, VD1 and VD2, average values will be the same. Average values are the same. But instantaneous values are different. But instantaneous values are different. They are not going to be the same. Because the instantaneous values are different, there will be some amount of circulating current that will be going to limit the increase in the circulating current. What we try to do is to have an inductance sitting in between the two converters and we connect the DC motor drive along with those inductance. So these are basically reactors or inductances for limiting circulating current. So although the average values are the same, we are not really going to limit the circulating current unless I have some resistance and inductance connected in the circuit. That is the reason why we are going to have these inductances connected in between the two converters. Before connecting the DC motor also, we will need this kind of reactors connected like this. So we are going to have, if you look at the voltage of the reactance, the voltage of the reactance is basically whatever is VD1 minus VD2. So if I try to look at what is the voltage across the resistance, reactance, this is plus and this is minus if the current is flowing in this direction. So you would be able to see VD1 minus VD2 as the voltage that is coming up as voltage across the inductance or reactance. So let me try to draw what is the voltage across the reactance. So what is the kind of voltage appears across the reactance? So this is alpha. This is going to be pi. Let me write this as alpha 1. Then you are going to have pi plus alpha 1. And we are going to have whatever. Okay, so this is the kind of time division you are going to have. So this is going to be alpha 2. because pi minus alpha 1 will be alpha 2. The same way this can be pi plus alpha 2. So if you look at the voltages, initially you are having VD1 to be negative, whereas VD2 is positive. So you are going to have a huge amount of voltage coming up as VD1 minus VD2. So this is going to be VD1 minus VD2. Okay, because this is zero voltage, so also is this zero voltage. But after that, this is increasing the negative direction, whereas this is increasing in the positive direction until this alpha. So this is alpha. Now, after alpha, this is also positive. This is also positive, and it is the same waveform which is corresponding to the supply voltage sinusoid. So that will continue until alpha 2. So this is going to be at zero voltage until alpha 2. Now at alpha 2, if you look at it, you are having a negative voltage in VD2, whereas you are going to have a positive voltage in VD1. So this is alpha 2, this is alpha 1, this is pi plus alpha 1. So VD1 minus VD2 is going to be a huge positive voltage. So VD2 is a negative voltage, whereas VD1 is a positive voltage. So you're going to have a huge positive voltage coming up from alpha 2 to pi. So this is going to be a huge positive voltage. And after that, you would see from this point onwards, from here onwards, you are having a positive voltage starting here. So this is going to be pi plus alpha. So this is going to be pi plus alpha 1. So from pi to pi plus alpha 1, if you look at it, VD2 is positive, whereas you are going to have VD1 to be negative. So there will be a huge negative voltage coming up again, and that will be appearing like this. Now from pi plus alpha 1 until pi plus alpha 2. So this is going to be pi plus alpha 2. So until pi plus alpha 2, it will be zero voltage. So again, it will be repeating itself like this. So this is pi plus alpha 2. So if you look at it, this is alpha 2 and this is pi plus alpha 2. This is going to be pi plus alpha 2. And at pi plus alpha 2, you have a positive voltage, whereas this is pi plus alpha 2 in which you have a negative voltage. So you are going to have again VD1 minus VD2 to be a big positive value, and then it will extend on the other side like this. So this is the kind of voltage you are going to get across the reactance. And depending upon what kind of voltage value you have across the reactance, L di reactor or I inductor divided by dt is going to be the voltage across the reactance or voltage across the inductance. So whenever you have a negative value, the current will be falling. And whenever you are not having any voltage, you may not have any current or you may have very minimal current. When you have a positive voltage, current will be rising, then it will be falling. So this is the kind of current you are going to have across the reactance. So this is the current in the inductance. So what happens is this inductance actually makes the current as continuous as possible. And because it is continuous conduction, that is where you are going to have 2 Vm by pi cos alpha 1 or 2 Vm divided by pi cos alpha 2. These values to be adhered to because you are going to have continuous conduction with the help of reactances that are inserted in the DC link along with the separately excited DC motor drive. So when you want to have first quadrant of operation, you are going to have, so when we want forward motoring, operation, then you are going to have alpha 1 less than 90 and alpha 2 greater than 90. So you are going to have, let us say alpha 1 equal to 30 degrees, then alpha 2 will be 150 degrees. You are going to have 150 degrees. So because of which the converter number 1 will be giving power to the separately excited DC motor drive, and you would be able to see motoring operation of this separately excited DC motor drive. And whatever is the circulating current, that is going to feed the power back to the beans. So this is going to work like regenerative braking zone, where it is going to feed back some power, whereas this is going to feed the power to the DC motor drive. So when you want to go from forward motoring to reverse motoring, what you would do is you would slowly increase alpha 1. So increase alpha 1 from, let us say 30, you are going to increase it to 40, 50, and then 90. And when you go to 110 degrees or something like that, when you go to a higher value than 90 degrees, you are going to have the reversal of the voltage here. This is going to become plus and this is going to become minus. At the same time, you would have decreased alpha 2. So when you decrease alpha 2, you would have initially been at 150, then you would have made it 140, then slowly it will come to 110 plus 70 degrees. So it would have come to 70 degrees. When it had come to 70 degrees, this will start working as a rectifier or motoring zone of operation. So this will have plus and this will have minus. And what you had seen as the back EMF originally would have been, back EMF would have had this as plus and this as minus. Now this is plus and this is minus, and this is also plus and this is minus. But when this was originally at, when it is at 110 degrees, you would see that slowly the motor's back EMF is decreasing. As the back EMF decreases, this will be able to actually take the current, because this, if you look at the original value of the firing angle, let us say alpha was 80 degrees here and alpha was 100 degrees here. For alpha equal to 100 degrees, still you would have seen plus here and minus here. So the current would have been able to circulate from the back EMF through this converter 2, and it would have gone back to the mains. So because of which you would have seen the forward motoring will slowly migrate to forward regeneration through converter 2. And as the kinetic energy stored in the motor drive decreases further and further, it will come down to zero speed and it will start accelerating in the reverse direction, provided the firing angle of converter 2 becomes less than 90 and converter becomes 1 becomes greater than 90. So you would see that the operation migrates from forward motoring through converter 1 to forward regeneration through converter 2, and then to reverse motoring. It is going to go into reverse motoring through converter 2. So slowly it will migrate from forward motoring using converter 1 to reverse forward regeneration using converter 2. When still converter 2 is working with alpha greater than 90 and converter 1 is working with alpha less than 90. Now eventually alpha 2 would have shifted to less than 90 and then it will go into reverse motoring mode. So it will allow a seamless operation of actually going from quadrant number 1, it will come to quadrant number 4, and then it will go to quadrant number 3, which is reverse motoring. This is omega m axis and this is TE axis. So this will be able to offer all four quadrants of operation. So just to reiterate, we should be able to say that uh, fully controlled converter gives two quadrants of operation. That is forward motoring and forward regeneration. Semi-converter gives one quadrant of operation, which is only forward motoring, whereas dual converter will be able to offer all four quadrants of operation as far as the separately excited DC motor is concerned. It is true for both three-phase case as well as single-phase case.